Downloading updates. And it's finalizing, so it wasn't my computer. That's great.
All right, any questions about the worksheet so far, anybody? Anybody have anything? Nope. We got something. Alright. So we start on one in particular? Yeah, I'm the first one. First one. Let me get you a the handout for the notes. So maybe if you want to actually good get it to really fast. See if that sparks the advantage.
Yeah, make sure you sign out. Okay. This is going to be finalizing forever, apparently. So I've been trying to find a backup plan. If you have your computer open, go to Google and just type in exoplanet database, or use your partner's computer. Database. And then the second result should be a website called Exoplanet Archive. Hi. Oh, sure. All right, so when you type in exoplanet database to Google, the second result should be exoplanetarchive.ipac. Click on that. All right, when you click on Exoplanet Archive, you should see a screen like this. See that? All right, there are some statistics up at the top. We'll just walk through them. This first number says that there are 1,821 confirmed planets. I don't think we're going to see very many pretty pictures with this website compared to the last one, but if you guys have smartphones, what you can do on your own time is download an app. It's just called Exoplanet, and it has all the information that we're going to be looking at. It has a database that's updated regularly, so it has all the same information that this website has, but with the smartphone app, it actually shows you an interactive map of where these planets have been discovered within our own galaxy. And you can zoom in and go to each individual system and see a lot of information in a prettier format than this website will. So again, it's just an app called Exoplanet. For now though, if we click on where it says 1,821 confirmed planets, it should bring up a table of information. All right. And this doesn't have the pretty pictures that the program would have had, but it has the same information. Has everyone navigated to this page? On the previous page, just that button up here that said 1,800 planets. Raise your hand if you're having trouble getting to the sheet that's on the board. All right. So again, this is kind of some dry information, but I'll walk you through some of it so you can see the range of different kinds of planets that we found. If we go to number of planets in system, I'm going to click this upper arrow so that it organizes the whole list by number of planets. And you see this list has all 1,800 planets that we know of. And if we're looking at how many planets are in that solar system, you know, we have 8 big planets and a lot of small objects. See, almost all of these have 1, 1, 1, 1, 1, 1. We've had a lot of planets that, to the best of our knowledge, are all by themselves. And if I go to the very, very end of the list, as it continuously has to load information. You see down at the very bottom, there are only a few systems that have 6 and 7 planets, even closer, anywhere close to our own. And these are individual planets. The solar system, look, these ones down here that say 7, those 7 entries are all from the same solar system. They're all from KOI 351 over here. So not very many solar systems with lots of planets. If you look at this column right here that I'm highlighting, it says discovery method. And if you just scroll through, what you're going to see is that, like I said, most of these were discovered using transit method, and the most of the rest were from radial velocity. Not very many examples of those other kinds that we went through at the very beginning. Orbital period in days. What is Earth's orbital period in days? 365, right. Do the years get longer or shorter the closer I get to the sun? Shorter, yeah. But still, even Mercury takes, I think it's 70 or 90 days. It takes dozens of days for Mercury to get around the sun. If I go to organize the list based on the length of its year by clicking on the upper arrow here, look, the shortest period of a planet orbiting another star is 0.09, so about 1/10 of 1 day. That planet is very, very, very close to its sun. It's way, way hotter and way closer than Mercury is. And there's a lot of examples of less than a day, around a day. So we found a lot of planets that are way, way closer to their sun than they are to, like Mercury in our solar system is. If I go all the way to the end and wait for it to load, which is very annoying, what you're going to find is we don't have nearly as many examples of planets that take a very, very long time to orbit their star systems. Why do you think it's harder to find a planet that takes a long time to orbit? They're slower, so how is that going to make it harder to find?
You have to wait for it to pass.
Yeah, you have to wait for it to pass. If I'm watching planets pass, and if Kepler only kept an eye on things for 4 or 5 years, it takes Jupiter and Saturn and Neptune longer than that to orbit the sun. So you're not going to see planets that are far away if they just so happen to not pass in front of the planets. Also, since it takes them a long time to go around, then it's going to take that star in the middle a long time to wobble back and forth or towards and away from you. So instead of seeing something rapid, you'd be seeing like a very slow measurement, and it's harder to realize that that's what's going on when you've only measured for a few years. This far column over here says planet mass as measured in Jupiter masses. So if it says 1, it's going to be the same size as Jupiter. If it says 2, it's going to be twice as big as Jupiter. And some planets, you just don't know how massive they are because of the way they were discovered. But most of them, you have an idea at some point, at least somewhere. Here we go. I'm not going to scroll through the whole thing because it takes time to load every single time, but if I look at that chart again, you'd find the same information that we found on that first graph. You'd find that most of them are big that we found, and not very many small ones have been found because, like Brendan told us at the beginning of the class, big ones are easier to see. If it's bigger, it has more gravity. So if it has more gravity, how is that going to affect the wobble? Yeah, it's going to make it move more. So the bigger the planet, the easier it is to detect. And also the bigger the planet, how is that going to make it easier when it passes in front of a star? Exactly, it's going to block out even more light than a smaller planet would. So the fact that we found more large planets than small planets doesn't mean that in the entire galaxy there are more big planets. It just means that the big planets are a lot easier for us to detect because they have a bigger influence on what they're doing. The planets that get people most excited are the ones that they find that are about the same size as Earth, more or less, and they're not too hot and not too cold. These are the ones that make people the most interested. Why do you think that is? Yeah, because life as we know it depends on a planet that's about the same size as us and that's not too hot and not too cold. So finding planets that are the closest as we found to having Earth-like conditions is exciting because these are the kinds of planets that, A, might hold some kind of alien life, or B, in the far future, when we finally make spaceships that are worth a darn, could be the most interesting places to go and visit in the far future. Since you don't have any program that gives you fancy pictures, let's go through a few lists of really strange planets that have been found that are really different than anything in our own solar system to give you an idea of the kinds of oddities that exist out there. All I did was type in list of strange exoplanets. There's a lot of lists. Number 1 on this list, a planet they call Kepler 10c. This means that it was the 10th solar system Kepler observed, and C means it's the second planet. A is the star, and they start numbering the planets B, C, D, E. So, Kepler 10c is a mega-Earth. What do you think that means? The Godzilla of Earth. A planet that has 2.3 times the size of Earth and is 17 times heavier. So the reason that's a big deal, Jupiter is obviously much, much bigger than Earth, but it's a gas giant. This is a big deal because it's so much bigger, but it's still a solid ball. It's still a place you could walk around on. It's a terrestrial planet, but it's so much more gravity, you'd be 17 times heavier if you stood on the surface of this planet compared to us. The smallest, Kepler 10b, that was 10c. 10b is the smallest known exoplanet, at least as of a couple years ago. Glassy planet. KOI 314c is the lightest planet to have both its mass and physical size measured. Surprisingly, although the planet weighs the same as Earth, it's 60% larger, meaning that it has a very thick atmosphere. So it's the same, it weighs the same as Earth, but it's bigger. So it must have a very, very thick atmosphere and be a different density than our planet. It's not very interesting. All right, here's the gas giant. It's almost twice the size of Jupiter. So look at the difference in size between Earth and Jupiter on the poster over there. And then imagine a planet that's twice the size of Jupiter. Okay. But this is one of those hot Jupiters we were talking about. Whereas all the gas giants in our solar system formed far away, this gas giant zips around its star every 3.5 days. So Jupiter's year is like 5 or 6, 7 of our years. This planet's year is only 3.5 days to go completely around the sun. There was another weird one that we just announced a couple of weeks ago, so it won't be on any of these lists. Which planet in our solar system has the big massive rings? Saturn. You know, they're the biggest rings in the solar system, but you still can't see them without a telescope. You can't just look at the sky and see them. They discovered a planet that has rings so big that if you put it in our solar system, where Saturn is, that the rings would be as big on the sky as the moon is. Some astonishingly huge rings that no one thought could ever exist like that before. This planet's 4,000 degrees because it's so close to its sun. I love this one. A planet that's orbiting not just one star, but 2 stars. So here's 2 stars that are close together, and then around them is a planet going around, which is fascinating because I hope we've all seen Star Wars and Luke Skywalker standing there looking at the 2 suns setting at the same time. So planet orbiting a binary star system. Let's go into this website's list, see what this says. Pink planet. A planet who the chemical signature you get from its surface seems to be a lot of diamond on the surface of this planet. Very close to its star. Planets like Earth. This one's interesting. This planet reflects so little light. It's so dark that physicists aren't even sure what it could possibly be made out of to make it so dark. It's darker than tar or pitch or coal. It reflects almost no light whatsoever. Oh, and one of these planets is so close to its sun that it's being blasted apart and melted because it's so close. So, see, there are a lot of strange examples of planets in other solar systems that are nothing like ours. So, the question is, how do these things form in the first place? How do I get stars so close or far away, or big or small, or differently? It's a brand new science field. This isn't something that scientists have been studying for like decades and decades. This is like in the last few years kind of stuff. We finally have telescopes powerful enough and good enough and technology good enough to be able to measure and find these things. So it's a brand new science field. Use those examples if you haven't already finished the final question there of brainstorming ideas. Use these to help you finish that. Does anyone have any final questions about the assignment?
How do we find the mass of planets?
Because when you detect how fast they're orbiting, there's an algebra equation which we'll actually use later in the semester that tells you, okay, if I have this planet here and this planet here, how fast should they be orbiting? Or vice versa. I see how fast they're orbiting, and I can find out how big this one is and how big this one is, depending on the orbital characteristics. They relate to each other.
More
Yeah.